Dr. Rico here. This is a lecture from my course, System Dynamics. The syllabus link is in the description. Welcome to the Laplace Transforms lecture, Properties of the Laplace Transform. The Laplace Transform has several important properties, several of which follow from the simple fact of its integral definition. We state the properties without proof, but several are easy to show and make good exercises, so I encourage you to do them. The first property is existence. As we have already seen, the Laplace transform exists for more functions than does the Fourier transform. Let f be a function of time on the non-negative reals to the reals, have a finite number, a finite magnitude discontinuities. If there can be found some real number m and some real number alpha such that this holds, and then transform exists, means it converges for sigma greater than alpha. Let's take a look at this equality a little bit closer. So we have the absolute value of f of t being less than or equal to m e to the alpha t for all t in the non-negative reals. Okay, so this is sometimes called being bounded by this exponential. And if this function is bounded by this exponential, then for some sigma greater than the alpha that defines this exponential, sigma is what determines whether the Laplace transform converges or not, right? It's the potentially envelope function on the rest of the transform. So if we have some sigma that's greater than alpha, it essentially means that alpha bounds the magnitude of f, and we have a sigma that bounds it even more. Okay, so if that is true, then there is a Laplace transform, that is, the integral definition of the transform converges. Note that this is a sufficient condition, not necessary. That is, there may be and are functions for which a transform exists that do not meet the condition above. However, if this condition is met, there is a transform. It's the old necessary and sufficient difference in logic, so it's good to review that from time to time. Linearity. The Laplace transform is a linear map. We had previously mentioned that it is a map of functions to functions, but it's a linear map, meaning that, defining that linearity in detail here, we have two real numbers, a and b, and two real functions of time. We also have f and g, the Laplace transform images of little f and little g. The following identity holds if you take the Laplace transform mapping of the linear combination, or superposition, sometimes called, of f and g being scaled by reals a and b and added together. We can simply take the Laplace transform of each f and g and combine those transforms in the same linear combination. Time shifting. Shifting the time domain function f of t in time corresponds to a simple product in the s domain Laplace transform image. Let the Laplace transform image of f, little f, be big F of s, and tau be a real number. The following identity holds. The Laplace transform of f of t plus tau, so a time shift of tau in the function of time, corresponds to the Fourier transform of the original function f before it was time shifted, multiplied by this factor e to the s tau. So essentially a time shift in the function of time corresponds to a product of the transform with e to the s times that time shift, tau. Great. Time differentiation. Differentiating the time domain function f of t with respect to time yields a simple relation in the s domain. Let f of s be the Laplace transform image of little f, and f of 0 the value of f at time equals 0. The following identity holds. The Laplace transform of df dt, the time derivative of little f, is equal to big F, meaning the Laplace transform of little f before it was differentiated with respect to time, times s. So the differentiation introduced this s product minus the initial condition, f of 0. Okay? For this reason, it is common to call this little s here the differentiator. Okay? It's a little bush league, but it is common to use that terminology. And I will occasionally use it, so I hope it's not too bush league. Okay. So, time integration. Similarly, integrating the time domain function f of t with respect to time yields a simple relation in the s domain. Let f of s be the Laplace transform image of f. The following identity holds. The Laplace transform of the integral of f is equal to 1 over s times the Laplace transform of f before it was integrated. This is the Laplace transform before it was integrated. The integration introduces this 1 over s factor, which is why we sometimes call this 1 over s factor the integrator. Convolution. The convolution operator, this asterisk, sometimes you see other sorts of stars used for it, is defined for real functions of time, f and g, by f convolved with g is equal to this expression, where f and g appear in the integrand of this integral, this improper integral over all of time. So this operation arises quite a bit in system dynamics, so it's good to look at this nice property of the Laplace transform. It also appeared in the Fourier transform. So this too has a simple Laplace transform. Let f and g, big F and big G, be the Laplace transform of little f and little g. The following identity holds. The Laplace transform of f convolved with g is the product of the Laplace transform of f and the Laplace transform of g, which is to say, convolving in the time domain is equivalent to multiplying in the s domain, which is a really simple operation, right? Just multiplication in the s domain. Whereas in the time domain, there was an integral that was not always easy to evaluate. So that does make it really nice sometimes to use this identity. The final value theorem. This theorem allows the computation of constant time domain steady state values from the frequency domain, which can be quite convenient when the inverse Laplace transform is elusive. I would like to qualify that it is the complex frequency domain. That is the S domain. Let f of t have transform f of s, and its time derivative have an existing transform. It means that the time derivative of little f also has to have a transform. If the limit in time exists, this limit in time exists, which is to say, if the limit as t goes to infinity of f of t exists, then it is equal to the limit as s goes to 0 of s times f of s, the Laplace transform of little f. Okay, note that if the steady state of f is not a constant, for example, if it's sinusoidal, The limit does not exist. Okay, so as the sinusoidal function goes to infinity, there is no convergence to a limit. So we cannot use the final value theorem because there is no limit. There's some sort of like Buzz Lightyear reference here that I'm missing, but all right. That's all I've got for you today. I'll see you next time.